Hey folks, okay. This time I want to get into looking at ways that functions can repeat themselves, can essentially run themselves over and over and over until some condition is met. So later on we'll take a look at loops as another way of getting repetition working, but for now, what we're going to do is set things up so that if desired, a function can call itself. Right? So if we've got some function foo, then inside foo it can make a call to itself to run itself all over again. And so we'll look at what the syntax looks like for this, how it actually runs, how it works, and how we can make use of it. So this concept of a function calling itself is referred to as recursion. So fancy term, just means that the function calls itself. So this is where we want to go. Now, there are a couple of things that we have to worry about. We have to provide a prototype, that sort of one-line shorthand version of the function first, and then later on, someplace further down, for instance, after the main routine, we give the full version of the function. Having that prototype allows it to refer to itself by name and to essentially call itself. So, usually the way this is used is either to get repetition in or to have a function kind of run itself over and over and over again, but passing simpler data to itself at each step. So the first call to the function has some complex, some big value, for instance, to process, and then it calls itself but passing a smaller value, and that one calls itself but passing an even smaller value, until you get to something that's so simple that it can just spew out an answer. So this is kind of the idea that we're going to go with. Now, to do this, the function has to know, under these circumstances, I should call myself again, otherwise I shouldn't. Right? It has to have some way of knowing when it should stop calling itself again. If you don't put that in, then it's just going to call itself over and over and over and over and over. You're going to get this kind of infinite cycle of recursion where it calls itself, and that one calls itself, and that one calls itself, and that one calls itself. And eventually, you just wind up getting the system crashing because you're out of memory because the function's called itself so often. So it relies on the use of an if-else statement to check whether or not it should call itself again. And that has to happen before it calls itself again to make sure that it knows when and how to stop. So that's one of the things that we'll take a look at. One of the things that we should probably introduce now that I don't think I've mentioned officially yet is how you kill a program that is out of control. So if you're sitting at the keyboard and you're running a program and you get something like infinite recursion or later on infinite loops, and it just seems to be spinning away and you can't get it to stop, if you hold down the control character and hit C, so control C, that will kill it and it'll immediately stop. So actually maybe let's take a quick look at a simple function where we'll do exactly that. Why don't we do some runaway recursion here? So let's call this runaway.cpp. I'm going to use, let's use cstdio just for the sake of argument. So we'll have our function that I'm going to call runaway, not for any good reason whatsoever. Run away, just some name for my function. And so I've got my prototype for it. This isn't going to return any data. It's not going to pass any parameters. It's just going to print something out. Oh, actually, no. Let's leave it at that. So we'll have our runaway function, my main routine. All it's going to do is call runaway and see what happens. And then my full version of the function, I'm just going to say it's running. So printf, it is running. And it will call itself. So again, this is the idea. The function can simply run itself. And what will happen is the main routine calls runaway. It comes in, does a print, and then calls itself. And that one starts running and does a print and calls itself. And that one starts running, does a print, and calls itself. And you get the idea. It just goes on forever. Each new call to the function does a print statement and then calls the function again, which starts that function, yet another iteration of that function, if you like. So we'll give this a whirl. So let's compile the beastie, runaway.cpp. We'll put it in runaway. Our executable will be runaway. We'll turn on our warnings for compiling and see how we go. So no errors, so we'll try running it. And away it goes. It's off to the races, and you can't really see it very well, but it's scrolling away like crazy, just printing. It's running over and over and over again. So I hit Control-C there to kill it, and it eventually stopped and gave this. Actually, it might have died there just before I hit Control-C. So the segmentation fault is usually when it winds up running out of memory and other fun and wonderful things. So that's an example of going through infinite recursion, right? Something that failed to check when to stop, and then using our Control-C to kill it. Okay, so this idea is that we need something to tell it whether or not it really should call itself again. So we'll refer to the base case as the condition where it should stop, where it should not call itself again. And then the general case, or there might be multiple base cases and multiple general cases, refer to all those ones where it does wind up calling itself again. So it needs to check for whatever this base case might be, see if it should stop, and if not, then do whatever it needs to do and do the recursive call. So it might be the case that the function does one thing in the base case, and then in the general case maybe it does that anyways, but it also does a recursive call, or maybe it does something else and a recursive call. But again, we can have these different cases that just revolve around the idea of whether or not it should also call itself. So what we'll do is have a look at a function that just counts down from some initial value. This time around it's going to count down from 10 and just print out 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. So we're going to use a function where we pass the sort of starting number as a parameter, right? So in the main routine, we're going to call print vals and we're going to pass it 10, basically saying, okay, start from 10 and count down. And for each call to print vals, it will print out the current value of n, decide whether or not it should stop, and if it shouldn't stop, then it will call itself again, but with a smaller value of n. So the first time through, it might print 10 and then say, okay, now I'm going to call myself with 9. And that time through, it'll print the 9 and call itself with 8, and et cetera, et cetera, et cetera. And the stopping case will be when it gets down to 1, we don't want to call ourselves anymore. We want to just print an end. So our print vals function here is going to be our usual, void print vals. We take the n that we're going to process this time around, and we'll have that base case, the stopping case, where it prints out the value but does not repeat anymore. So if n is less than or equal to 1, we'll just print out the current value of n. If n is anything bigger than that, so our else case we'll print out the current value of n, and we'll run the function again with n minus 1, with a smaller value of n. So again, what's going to happen is it'll print out the 10, for instance, and then call itself on 9, and then that call to print vals 9 will begin running. And each of these, if you like, is an entirely separate call to print vals. So each one runs on its own, completes, and eventually returns. So in this case, this should go through and print out 10, then 9, then 8, then da-da-da-da-da-da-da-da. Eventually it makes a call to print vals 1, prints out the 1, and ends. And at that point it kind of unwinds. The call to print vals 1 ends and returns control to print vals 2, which ends and returns control to print vals 3, etc., etc., etc. Eventually, this returning chain comes all the way back to print vals 10, which ends and returns to main, and the main routine can finally end. So let's actually give that a try. So let's try our runaway again. Only this time we'll throw in our print statements. So let's say so this is going to do essentially what we were just talking about. We'll get it to start with a value of 10. Each time through, it's going to print the current value. Oops. Stopping when it gets down to a 1. So if n is less than or equal to 1, then we'll, well, I'll do a printf this time since we were sitting there with C standard IO anyways. So we'll print the current value of n. So let's say that current n is, and we'll print it out. And then otherwise, let's do this. Let's say the current n is, so we'll print out the current value of n, and then we'll call runaway, but we'll pass it a smaller value. So, you know, the first time through we'll pass the 9, second time through we'll pass the 8, etc., etc., etc. So each time we'll call runaway with a smaller value. And in theory, sooner or later, it should get back to that, or should get down to that base value and stop printing out. All right, so we'll try compiling this beastie, and we'll try running it. Right, and it's going through, and you can see how it's going through the sequence of each successive call. Now, it might be handy to see how all of this kind of unwinds. So when we make our recursive calls, right, we do our printf, and then it goes off and runs the recursive version. Right, it runs runaway on 9, or runaway on 8, or runaway on 7. So eventually, you know, those things are going to go off and run to completion, so they're going to do whatever they need to do. They're going to make a recursive call that goes off and, you know, has to wait for it to complete, and it makes a recursive call, and we've got to wait for that to go off and complete. But eventually, that long chain of recursive calls completes and comes back to wherever we are right now. So let's just show that here as well. So let's have our recursive call. So we're going to do a print statement, and then do a recursive call, and then we're going to have another print statement that shows when we got back. So, you know, we're now back at n is %d, just so you can see where these calls kind of begin and end. So we're going to do our print, we're going to do our recursive call, and then we're going to tell, you know, when we get back to n is 10 or when we get back to n is 9. So we'll compile again, and we'll run it again. And so you can see it does the call to 10, or call with runaway 10, calls runaway 9, calls runaway 8, etc., 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 etc. And then eventually runaway 1 finishes and goes back to runaway 2. And then eventually runaway 2 finishes and goes back to runaway 3. And so you can see how we get deeper and deeper and deeper and deeper and deeper into these recursive calls, and then gradually they unwind and we start coming back to the very first one. And eventually we wind up back at the main routine. Here, we can even throw that in as one more step. Let's say we'll do a printf, you know, starting in main. And so we can see where that comes in, and a printf to show where we're finishing in main. And we'll compile it, and we'll run it. And again, you can see that we started in main, we got deeper and deeper and deeper and deeper and deeper into the recursive calls, and then gradually we started working our way back towards the beginning and eventually wind up back in main. So you can start seeing how these things work their way deeper into the calls and eventually come back. But when you're going through and trying to understand your recursion, that's a useful thing to keep in the back of your mind. All right, let's see. So this is actually walking through pretty much exactly what I just described, where how that countdown works, right? The main calls print vals 10. prints 10, then calls print vals 9, and it has to wait for print vals 9 to complete. So print vals 9 prints 9, then calls print vals 8, and it's got to wait for print vals 8 to complete. And you just go deeper and deeper and deeper until eventually print vals 1 gets called, does its print, and then it's finished. And so it comes back to print vals 2. And then print vals 2 can finish and returns to print vals 3. And so again, we just work our way back, and eventually you come all the way back to the main routine. So that is what's taking place with these deep sequences. So, a bit of an uglier slide here. The notion here is the same, but what we're going to do this time is get the user to keep trying to enter an input value until they give us something valid. So, I want the user to enter a positive integer, an integer that's greater than 0. So, what I'll do is I'll prompt the user, I'll attempt to read what they type in into an integer. If it fails, then I'll do my cin.clear and cin.ignore. Otherwise, I'll check and see if it was actually greater than 0, and if it wasn't, I'll prompt them to try again. So I want to go through this cycle of, check if it failed, or check if it was just kind of out of range, or if it was actually valid. And so, the basics are pretty straightforward, right? Our usual, we'll go with the IO stream this time, so we'll do our IO stream and using namespace standard, and I'll have my function to get a positive integer, and it's just going to return an int, whatever the valid int eventually was. So this is going to keep recursing. It's going to keep going off and off and off and off and off until eventually they give a valid value, which is going to get passed all the way back this recursive chain till eventually it comes back to our main routine. So I'll have a variable to store the eventual valid answer in, and I'll say my valid answer goes into, or my user val is the result of a call to get positive int, and then we'll print it out. So by the time we get back here, it will be because we actually have a valid value. But it might take a lot of tries before we actually get that from the user. So this get positive int routine is going to ask the user, please enter a positive integer, have a variable stored in, and try reading it in. And then we have to see if it works. So if it failed, so we'll check cin.fail first, that means that they entered complete garbage. It wasn't an integer at all. So we'll give them an appropriate error message, say that wasn't an int, and then we'll ask them to try again. But again, because it failed, we have to get the garbage out of the input. So we'll do a cin.clear and a cin.ignore. So that's got rid of the garbage that they typed in, and now we can actually get them to try again. So here, we'll call getPositiveInt again, and that will go off. And again, that's a brand new call to getPosInt, so it's going to go through and say, please enter a positive integer, and it's going to try and read it in, and it's going to see if that one failed, and it's going to go through this cycle, right? So we'll just go through as many calls and as many recursive calls to getPositiveInt as we need to see where we wind up. Now, if the cin didn't fail, then it's because it read in an integer. We should check and see if the integer was actually greater than or equal to 1. So if the value was less than 1, it was too small. So we'll give them an error message, and we'll ask them to please try again. And again, we call getPosInt because also in this case, we don't have a valid number yet. We've got to go off and get one. So in these two cases, right, the two recursive calls, it's saying, well, I don't have a valid number yet. Call getPosInt yet again to go off and get one. And again, it might have to call getPosInt again, that might have to call getPosInt again, that might have to call getPosInt again, but eventually, somewhere way down the chain, the user's going to get tired of typing in garbage and is going to at least accidentally type in a valid integer, which gets passed back and gets passed back and gets passed back and gets passed back, until eventually it winds up here, and we'll store it in val. So we wind up with either the user gives us a valid entry in the first place, which goes in val, or they give us garbage, in which case we do a recursive call, which eventually goes off and gets a valid value that we put in val. Or they enter something that's out of range, and we get them to try again, and this goes off and does recursive calls until eventually something valid comes all the way back, and we put it in val. And so our third case, we'll just tell them, oh, hey, yeah, wonderful, that was valid. So we have this kind of chain of three possibilities. Either we need to do a recursive call because it was garbage, or we do a recursive call because it was out of range, or it was okay and we don't need to do a recursive call. So from from any one of those three paths, eventually we get a valid answer in val, either because they gave it to us directly or because we got it through kind of one or more recursive calls. And so finally, we can just go through and return that valid value. Now, one of the most common errors that you're going to run into when you're doing this sort of recursive call process is you make your recursive call, but you forget to store the value when it comes back. So that is one thing that we'll want to watch out for. All right, maybe let's just do a quick play with that just to confirm that this kind of works the way we're expecting. So let's do a getInt.cpp, and okay, we'll do our IO stream this time around. So using namespace standard, and so we'll have our get an integer routine. And at first, let's just settle for any old integer, and then we'll tweak it for wanting a positive one. So we've got our main. Let's just throw in a comment here saying that get an integer from the user, repeat until they give one. In our main routine, we'll have the place where we're going to store it, and we'll say x is equal to get integer, and we'll do a cout. Your final answer was, and whatever x is. So we'll have our full version of getInteger, if I can learn to type. Please enter an int. I'm just going to use v for this, and we'll do a cin into v. And again, it might have failed. So we'll say if cin fails, then we'll do something. Otherwise, we'll say it's okay. So let's give this a try. If cin fails, then we'll tell them that was not an int. We're flushing the input. We'll do our cin.clear to clear that error flag, and our cin.ignore to get rid of a bunch of, essentially to try and get rid of a line of garbage. And maybe we'll tell them, please try again. And again, if they try again, well, they will have to try again because the program's going to wait for them to. But when they try again, we'll make the recursive call and store what comes back. So we'll say v is equal to get integer. And so that's going to get whatever comes back from our repeated attempt. So maybe we'll just leave it at this for now, and then we'll show the return in a second. So otherwise, we'll say thanks for integer and whatever's in v. And again, our function needs to return the valid value once we get it, so we'll return that v when we eventually get one. So let's try our compilation. So we'll compile getInt.cpp. We'll put it in a getInt or executable. We'll turn on our warnings. And woohoo. Okay, so let's try our getInt. And so I type in blah. And it says that wasn't an int, flushing the input, and please try again. And so that new second call to getInt, the recursive call to getInt, is now waiting for me to enter an integer. So I type in garbage. I can't type, but it's still garbage. So again, it tells me that wasn't an int, flushes the input, waits for me to try again. So maybe this time I turn around and say, okay, well, here's 50. And so it winds up returning 50 from that last recursive call, which gets returned to the middle recursive call, which gets returned to the first call, which gets returned to main. And again, if we want to kind of see how that works out, we can throw in an extra cout statement in here after the recursive call, where we can say, the recursive call gave back, and we'll print out the value that we got back. And so again, we can kind of see the recursion unwinding if we do it this way. So again, if we try the same thing, blah, garbage, it's going deeper and deeper down the rabbit hole, ick, and then eventually I give it some valid values. And so, we enter the 75, it says, thanks, that was valid, and so that's from that deep nested call, and it returns the 75 to the one before it, which returns the 75 to the one before it, which returns the 75 to the one before it, which eventually gives the 75 back to the main routine. And so you can see this process unwinding. All right. So again, we will play with different aspects of recursion as we go along. There are times when you can come up with a really simple recursive solution to a problem where the other solutions, the solutions using loops, which we have yet to study, aren't as elegant. But there are some drawbacks to recursion. And so I wanted to just mention some of the efficiency issues and why we won't wind up using recursion for most of the repetition that we play with. So whenever you make a function call, while that call is running, the system has to set up a little bit of space for that particular call's parameters and local variables. And so there's this little chunk of memory that's being set aside for that current call to that function. So if we had something like our printVals10, where the call to printVals10 also called printVals9, which called printVals8, which called printVals7. So each of these things has their own little chunk of memory set aside for that individual call's parameters and local variables. So by the time it got to printVals1, there'd be 10 of these little templates set up with storage for parameters and local variables. If you called printvals with a really big number, 100,000 or 1,000,000 or 1,000,000,000 or whatever it might be, then by the time it got down to printvals1, you'd have 1,000,000 or 1,000,000,000 of these things floating around, and they're all sitting there taking up space in memory. They're actually sitting on the call stack or the system stack, which eventually, if you have enough calls and they're taking up enough space, you'll run out of memory and it's going to crash and die. And you might get a stack full or stack overflow error, or you might get a segmentation fault error, but you're going to get some kind of a crash and an error. So usually what we will try and do with simple repetition is to use a different structure, a looping structure that allows the repetition without having to make entirely separate function calls every time. But we will get there probably early next week, I would think. All right, that is where I will leave recursion for now. Again, we'll play with examples of it as we start getting into different applications here.